Well, we're on time now.
Okay.
Ekis. From the Llano Estacado to the Rio Grande Valley, from the bayou to the bottomlands, from the desert to the rolling plains, this is a seminar for a wide range. Welcome to the Soil and Crops Hour of Power. Today's guest comes to us from the great enchilada producing region of far West Texas. Dr. Schwab, would you like to introduce our guest?
Cannot possibly follow that.
Yes.
I'll give it a shot. Thanks for setting the bar pretty high there, Scott. Anyway, it is my pleasure to introduce Girisha Ganjegunte today. He is, as indicated by Scott, he's out in El Paso and is a professor and has carved out quite a niche for himself in studying the impact of salinity on growing crops, as well as urban wastewater, et cetera, et cetera. This is an area of great need in his area of the world out there, and he's done quite well with that. He's got over 40 publications that are well cited and well received, and I will not get in his way any further. So Girisha, it's a pleasure.
Yeah. Thank you. So I can share my screen here, right? Let's see if I can figure it out. Okay, can you see the first slide?
We see it perfect.
Okay, yeah. Thank you. That was a great introduction and great announcement. It's hard to match that, but I'll try to do my best. So I would like to start by thanking my team members. Vijay is my postdoc, and I have 4 part-time students. We don't teach, but we do hire students to carry out research work from local, the students usually study at the local universities. So for those of you who are not familiar with my part of the world, this is the map of USA showing the location of Rio Grande Basin. It's the 5th largest river. It irrigates hundreds of thousands of acres before it joins the Gulf of Mexico. The area I'm located is close to El Paso. It's supported by the irrigation comes from Elephant Butte Reservoir, and it irrigates over 178,000 acres in southeast New Mexico and far west Texas. The county downstream of El Paso is called Hudspeth, and they're not party to they don't have water rights, but they do use the drain water, the drainage or the return flows coming from agriculture fields from the upstream. That supports about 18,000 acres. So all in all, it supports over 200,000 acres of agriculture. It's by far the dominant source of irrigation in the region. However, the region is also experiencing a lot of urban population growth. And as you can see from the statistics, in the last 100 years, the population has gone up from 44,000 to 2.5 million. And mind you, this is like 10 years old data. So the population is much higher. So with the increase in population, we also have a lot of demand coming from urban sectors. El Paso is, in general, the middle Rio Grande area is getting rapidly urbanized. And so the competition from urban sector for fresh water is also increasing with time, which is evident from this graph. Agriculture by far is the largest water user. As you can see, the dominant crops grown in the region use a lot of water for successful completion of life cycle. You can see, everywhere else, the water depth is measured in inches or centimeters, but in El Paso, it's in feet. So you can see alfalfa, pecan require about 5 feet, 60 inches. Pima cotton, which is the extra long cotton, very common to this area, requires around 3 feet of water. We used to see a lot of lettuce, vegetables like onion, green chili, but nowadays, because of elevated salinity, all these are failing, and they are confined to maybe southeast New Mexico. I haven't seen these crops in El Paso for a long time. The reason for elevated salinity is because the river water we get from Rio Grande becomes progressively saline as it as it moves away from the headwater. You can see less than 500 ppm of salinity somewhere where it originates, and by the time it hits El Paso, it's well over 1,000 ppm. So this exceeds, those of you who are familiar about drinking water standards, salinity has a secondary standard of 500 ppm, and both in summer and winter, the river water salinity it exceeds that secondary limit. So salinity is a major quality concern associated with the dominant source of irrigation water. And the reasons for elevated salinity of the river water are both natural and man-made. Natural because when the river hits some geological formations, it picks up a lot of salts on the way, and also upwelling of geothermal wells, of springs, and they are saline in nature. And we also have big major cities like Albuquerque, Las Cruces, before El Paso and the upstream. They use a lot of water softeners, and water softeners have a lot of sodium chloride, and they add to the salt salinity of the river water. And the return flows coming from upstream agriculture, irrigated agriculture fields, rejoin the river and becomes part of the supply. So they all progressively make the river more saline. So in the recent years, along with salinity, we are also seeing extreme weather events, probably due to climate change impacts. And during the full year, Elephant Butte looks like this. And in drought years such as 2013, you see very low water accumulation. So during those periods, growers usually depend on groundwater for supplementing irrigation because three major crops are perennial, so we need to salvage it. Pecan is a dominant, it's a very dominant cash crop. It's a nut crop. It takes about 8 years to produce yields. So if you kill the tree because of lack of water, it's hard to make profit, and the growers may stop growing, but the bank payments won't stop. So they got to salvage these trees. For that, they use groundwater, but unfortunately, there are like many sources of groundwater. It's surprising that El Paso, being such a dry area, which receives only 6 inches with a potential evapotranspiration of close to 80 inches, has huge reservoirs. Huayco Bolson, Mesilla Bolson are the dominant water, groundwater sources, dominant aquifers. Actually, El Paso is home to the largest inland desal plant. And the problem with that water is it's brackish, it's saline. You can see the salinity of the groundwater increases with the depth. So near the river, the sediments, maybe the shallow groundwaters are actively, exchanging river water with, there's a lot of exchange between aquifers and the river in the shallow depths. So water is almost close to river water quality, but deeper you go, more brackish it becomes, and beyond certain depth, it hits almost seawater kind of salinity. So the actual irrigation, the Elephant Butte reservoirs was constructed in early 1900s, and the actual irrigation started in 1920s. Within 30-40 years of irrigation with the river water, you can see large portion of the valley became saline. that's because of the elevated salinity of the river. And also we are located in a dry land, arid ecosystem. So a lot of salts that were formed as a part of soil formation processes are still there in the soil, never had an opportunity to dissolve. So when you apply irrigation water, now they have an opportunity to dissolve, and high evaporation helps in accumulation of these salts in the root zone. So the effects of salinity are multifold. Generally, it decreases water availability to the crops. Then it results in lack of germination, poor stand, stunted growth, and necrosis because it burns leaf tips. If direct spraying will also kill the leaves, resulting in low yields and low crop quality. So sodicity, which is like the dominance of sodium. If sodium is the dominant salt present in the water or in the root zone, results in destruction of soil structure, poor permeability, anoxic conditions, and ponding of water. Even though the grower may be applying a lot of water, but it won't be reaching the roots because of this surface ponding. So to address all these concerns, my program has 3 focus areas. To reduce the water footprint, I'm looking at improving on-farm water use efficiency, irrigation water use efficiency. Then there's plenty of opportunities for water reuse, and obviously salinity management is required. So to look at the projects going on or have been completed under this topic, it's clear that some of these efficient systems like surface drip or surge irrigation, even sprinklers, have potential to reduce amount of water required to grow the crop. This is an effective alternative to common method of irrigation prevailing in the area, which is basin flooding. But the growers are concerned about the yield and also salinity. So many growers think that flooding is required to leach or flush the salts below the root zone, so it won't accumulate. So they are very hesitant to adopt, water use, like more efficient irrigation systems. To alleviate that kind of concerns, I have been developing information on salt accumulation under different irrigation systems. There are some progressive growers in the region. They have adopted surge irrigation, surface drip, subsurface. So I've been comparing salt accumulation under different irrigation system for the same crop with similar water quality, like water having 1 decisiemens per meter. So under basin flooding, which is like this one, the most dominant method of irrigation, the maximum salinity observed was about 6 decisiemens. Salinity can be measured in 2 ways: by conductivity or electrical conductivity, and as a total dissolved solids. So approximately these are interchangeable, and an EC, 1 decisiemens is approximately equal to 640, 650 ppm. It changes with the type of salt. So all these fields were irrigated with similar type of water, but using different irrigation system. So under traditional irrigation, the maximum salinity was 6. Under surge irrigation, around 4. Surface drip, where you apply water close to the tree trunk, the crop that was grown in all these 3 fields was pecans, because it uses a lot of water. So if we can save water in that, we can extend the availability of fresh water. Surface drip had the lowest among different irrigation systems. Surprisingly, subsurface drip, which is practiced in some urban landscapes like golf fields, had maximum salinity of 9 decisiemens. That's because in surface drip, salts are flushed, they are leached below the root zone when you apply water at the top. Whereas in subsurface, it dissolves salts present in the subsoil, and because of high evaporation, it actually drags those salts along with it. The soil water solution can help in accumulation of salt at the surface. Water leaves the surface because of the evaporation, but salts stay on the top. So if the cost and salinity are the concerns preventing growers from adopting some high efficient irrigation systems, we also looked at better scheduling of irrigation. That the most common method of flood irrigation here, like scheduling flood irrigation, is depending upon the texture of the field soil in the field. They count number of days and just apply irrigation regardless of soil moisture content. As you can see, the field capacity is around 0.37. So about 12 irrigations were applied, and most of the time, before we started looking at scheduling irrigation based on soil moisture content, it was much higher, than what is required by the crop. So depending upon maximum allowable deficiency of the root zone moisture content, we set some trigger for, scheduling irrigation. Using that, we could reduce the number of irrigations from 12 to 10. 2 irrigation savings can roughly translate to 10,000 acre feet of water per year, just for pecans. So if cotton growers start doing it, we can see a lot more water, savings. So to address the concern of growers about, reduced yield because of reduced water application, we also looked at the nut production during pre-steady and steady period. Basically, it's for those of you not familiar with pecan crop, it's an alternative bearing crop, meaning 1 year it bears a lot of nuts, the next year maybe half of it. So the dashed line here shows average, like long-term nut yield per acre during off year, and the solid line is during on year. If you compare pre-steady and during steady period, which is like using improved irrigation scheduling, there was not much difference. In fact, in many years, the yield with less water was greater than that during pre-steady years. So both salinity, the fears associated with salinity accumulation and reduced nut production are not well founded. So this kind of data can help in motivating growers to adopt more efficient irrigation systems. So the next topic is water reuse. As you can see there, in addition to Rio Grande River water, we also have treated municipal wastewater and like I already mentioned, brackish groundwater. So the major quality concern is salinity and sodicity of these waters. El Paso is one of the largest cities in the West, Texas, and annually it treats about 60,000 acre feet of water, municipal wastewater, and almost to drinking water standards. Actually, type 2, like some of these treated waters are supplied to urban landscapes, and they usually have very low BOD, COD, and some elevated nitrogen phosphorus content, so which can be beneficial for agriculture users. Of the 60,000 acre feet, only 13% is reused for urban landscapes or nurseries, things like that. So there's plenty of opportunity for putting this to good use to supplement, irrigation during drought years. Similarly, groundwater, if we can find a way to use the saline brackish waters, there's plentiful of water available in the region. So to do that, it's necessary to diversify the cropping pattern, existing cropping pattern. with some crops that can tolerate higher salinity and also use less water compared to traditional crops. During the periods of drought, a lot of growers fallow their field, especially under annual crops, because there is not much water, enough water to grow these crops. However, if we can use less water and maybe supplement with treated wastewater or salty water, salty groundwater, we can get some farm revenue even during the periods of drought. To this effect, we have been looking at salt tolerance of different bioenergy crops and also food crops to diversify the current cropping pattern. This is energy sorghum. As you can see, it really flourished well under saline condition. Canola is grown during the winter, so like it's a winter crop, so we try to grow in fall. This was replicated in many locations. This is the growth in West Laco. And along with sorghum, we also tried switchgrass. Quinoa is something my postdoctoral scientist is evaluating under greenhouse conditions. So the results have been very encouraging. Sorghum, on an average, produced about 2,000 grams per square meter, so roughly 20 tons. Switchgrass is about 9 to 10 tons per acre. I think 9 to 10 tons per hectare. I think it's gram per meter square. And canola was around 1,700 pounds per acre, the seed yield. So it's very comparable to what one can get under non-saline conditions elsewhere in the country. So I think these crops are highly tolerant to salt stress, so have potential in this area. I think the quinoa yields are not available. We just started harvesting. Our rough estimate is about a ton per acre. So a pound of quinoa is selling for about $2 a ton. It has a good potential to even to replace pecan if the soil becomes too saline. And at the end of this 3-year study period, we looked at salinity changes. As expected, salinity of the root zone increased under wastewater irrigation in some plots, but they were all under the threshold limit. Surprisingly, the salinity of gypsum applied plots were higher, but this is a good type of salt because gypsum has calcium sulfate. More calcium will help in better aggregation. We are also looking at the soil quality changes as a result of wastewater or alternative water irrigation compared to fresh water with or without gypsum and sulfur. The wastewater did not really show much difference in organic carbon stock or epoxy or mineralizable carbon, so nitrogen. So it may be too early to say, but we are not seeing major differences. So this is a good news because wastewater can be successfully used to grow crops in this region. So the third focus area is salinity management. The goal of any successful salinity management program is to keep the salinity of the root zone under the threshold of the intended crop. So beyond that, as the salinity increases, the crop yields can decrease. So that's not, a good situation. So salinity management starts with selecting appropriate crop or cultivar. See, we all think alfalfa is super sensitive to salinity. I think Calvin collaborated with me. In this, I'm thankful to him. And this is a variety from, I think, Arizona, California, so that area. So this performed very well under elevated salinity and produced close to 8 tons per acre, which is comparable to what we are getting under non-saline conditions. For nut crops such as pecans, one can look at rootstocks that are highly tolerant to salt stress, and graft a high-yielding scion on the top of the rootstock. So that's a good management way of method to produce some yield. And ongoing research collaborations, with I think Jane Dever at Lubbock and also NMSU is evaluating salt-tolerant cotton crops, cotton varieties. We all think cotton is salt-tolerant, but some of the fields, maybe nearly half of the fields in El Paso, exceed the tolerance limit for cotton, which is around 8 deci. So research in that direction is welcome. Along with appropriate crop and cultivar selection, leaching is another method of controlling salt accumulation within the root zone. This involves applying additional water, water in addition to crop needs, to flush the salts to deeper depths. And this the prerequisite for that is well-drained soils. So there are many formulas to calculate how much extra water is required, depending upon the root zone salinity and the salinity of the irrigation water. But again, it depends. It requires the soil to be in good drainage, in drainable condition. So in many fields which are like both saline and sodic, tillage, saline and fine textured soil, we can use tillage methods, and this is one of the popular ways of managing salinity in cotton crops. In the early stages of the crop, it's around germination stage, it's very vulnerable to elevated salinity. So the growers have a way to attract all the salts, most of the salts in this hill to the top of the hill by applying water, dissolving the salt, and because of high evaporation, they all accumulate at the top, and they come back and they break that hill, resulting in less saline environment around the seed, so it starts germinating. So this is a low-cost method of controlling, and it's very popular. In perennial crops such as pecans, one can look at loosening the heavy soils, mostly found in the agriculture fields of El Paso and in Middle Rio Grande, because the soil is deposited by the river. It's alluvium, so alluvial soil. So it actually helps temporarily. This is like, it can go up to 18 inches. And in the more extreme conditions, one can look at using excavation method, because the river was meandering in the past. Now they have built canal to stabilize the river. We can see alternative layers of sand and heavy texture soil on top of it. So because the clay soils have poor permeability, growers resort to excavation. So they can dig like 8-10 feet and mix both sand and clay layers to get a favorable tilth. That will improve drainage and also helps in leaching of salts. So this provides some comparison and the effectiveness of different tillage practices on salinity reduction. In most cases, the salinity decreased by half. So it all works, but the effect is, the data is not presented here, but the effect lasts longer under excavation. It's expensive, but also it's more effective. So to sum it up, the effects of tillage are immediate. It improves soil permeability for short period, but with the exception of excavation. Disadvantages are it's very expensive and also can bring salts from deeper depths to root zone. Another research, another method of improving soil permeability soon after by applying polymer. Soon after the tillage, there will be favorable tilth. This can be preserved. If we don't apply anything, it would vanish within 2-3 years. But if we apply a polymer like anionic polymer, the most common one is PAM, you can see it gets coated, and the polymer kind of glues these particles together, keeps the drainage, and that's evident from lower salinity in the polymer applied tabs. These are all 10-acre tabs of pecans, and compared to traditional method of controlling sodicity, which is gypsum, polymer is doing much better. So when it comes to salinity is one thing, but when it comes to sodicity, one needs to change the exchangeable cation, dominant exchangeable cation on the soil clay complex. In sodic soils, we often see the dominance of sodium ion, which is not good for permeability. So the most common way is to replace sodium with calcium by providing readily available calcium sources such as gypsum. Because we have a lot of calcium carbonate in the soil profile, growers apply elemental sulfur and sulfuric acid to convert calcium carbonate to gypsum, and that gypsum would, with the hope that the gypsum would replace sodium on the soil complex, cation exchange complex, with calcium, and apply excess water to leach the sodium below the root zone. So this helps, which is evident from application of gypsum helps, as evident from this picture. This is a cotton field located right next to my office. As you can see, the SAR of this field, 30 acres field, had a maximum value of 30. And after application of gypsum, we went back to the same field after 2 years. The SAR had reduced to less than 8. So the threshold for sodium adsorption ratio, that's what SAR stands for, is 13. So I think in clay soils it can be as low as 6, but this is a loamy soil and it works. As a consequence of better drainage, even the salinity of the field went down. See, before the application, it was around 10.5 deci, and cotton is the crop grown in this field. So the threshold is around 7.7, and after gypsum application, it reduced by half, or less than, like more than half. So the maximum EC of this field after gypsum application reduced to around 4.5. So gypsum works, but the issue with gypsum is it's expensive. Gypsum costs around $32 per ton, and growers apply 4 to 5 tons every third or fourth year. So it can add to the cost. So an effective alternative would be like using native calcium, which is already present in the soil profile. So according to NRCS, about 10% of the soil weight is calcite or calcium carbonate. We also call it caliche. The solubility of caliche is low in fresh water, but it can increase in dilute acids. So as you can see, there's plenty of calcium carbonate in the agriculture fields in the top 3 feet. So growers, especially pecan growers, apply about half a ton to ton of sulfur, elemental sulfur, in the hope of converting that to sulfuric acid, and that sulfuric acid eventually reacts with calcium carbonate to make some in situ gypsum. But in reality, it seldom works, because the most common problem with sodic soil is anoxic condition, as you saw, ponding of water, which doesn't provide oxygen required for conversion of sulfur. So farmers resort to short circuiting the whole thing. So they kind of apply this concentrated sulfuric acid, which is mixed with the irrigation water in the ditch before it hits the entry point somewhere over there. So it dilutes and it works because it's sulfuric acid is already, there, and it can react with calcium carbonate in the soil, but it's very dangerous. It's 92% sulfuric acid, and during the most dangerous part is transferring from the supplier to these tanks. A lot of accidents have happened. So instead of that, one can look at a safer alternative such as sulfur burner. These machines can burn sulfur and convert sulfur to sulfur dioxide, trioxide, sulfurous acid, and then sulfuric acid. But it's a very dilute sulfuric acid. It's like 0.1 molar. It's safe. Even if somebody gets sprayed with that water, it's not going to burn or kill them or impair them. So it's much better to apply dilute sulfuric acid than concentrated. And it also works. This is a study that evaluated the effects of sulfur burner treated water on cotton field salinity. This should have been there was a title here. So the heading is before application of sulfur burner. We could see the maximum salinity of 13 deci. Mind you, this cotton has close to 8 deci. So a lot of areas in this 30 acres field was exceeding, they were higher than the threshold for cotton. But after 1 year of irrigation with sulfur burner water, about 33 inches, you can see a lot of areas turning green below the threshold of cotton crop. So it works. So there are many ways. This is the last slide I want to present. I want to highlight the current and future research. So we all recognize in our team, and the collaborators recognize diversifying the cropping pattern to handle elevated salinity. As more and more areas become urbanized, or water availability reduces because of extreme events, we probably have to depend on brackish groundwater and municipal wastewater and alternative waters like that. So one needs to have a better cropping pattern that can handle it. Then there are we are going to work on management strategies. We have been working on it, and we are going to work on that in future too. I don't have time today, but we are also actively working on managing salinity issues in urban landscapes. Then we can also, a lot of people look at wastewater as a problem, and El Paso Water Utility spends lots of millions of dollars on bringing down the ammonia or phosphorus levels in this water. But we are looking at ways of harvesting these nutrients, adding that to compost, and making a slow release fertilizer compost for beneficial uses. So another ongoing project is to evaluate soil quality parameters under elevated salinity. I've been teaming up with chemical engineering and other engineering disciplines to look at desalination potential of brackish water for agriculture purposes. We also have a new faculty whose expertise is in remote sensing and UAS, and the idea of this research is to monitor and manage crops, crop stress, soil salinity and quality, widen the research to include basin level salinity management. So in conclusion, improving water use efficiency, water reuse can extend the freshwater availability. All this will help in ensuring long-term viability of irrigated agriculture and also meeting urban demands. High TDS water irrigation is the major source of salinity in the region, but successful agriculture is possible. There are many management options available, but it all boils down to cost. So with that, I want to thank my collaborators, and I'll be happy to answer any questions you may have.
Great job. Great job.
Thank
Thank
you.
you very much. Questions?
I have a question. This is Mark McDonald.
Yeah.
So some plants can be used for like bioremediation and accumulation of toxins. Is there any research to potentially utilize those type of plants as maybe a cover crop in the off season to accumulate some of the salt present and then just remove it from the field?
Yes. In fact, all those bioenergy crops that I showed in that slide, energy sorghum, switchgrass, they have a higher ash content, like 10% by weight. And we also looked at barley, that's a hyperaccumulator of salt. So even Sudan grass is a very good accumulator of salt. So yes, we are looking at that. And I have many more other area like issues that we have been working on, but within 40 minutes, I thought this is most relevant. And yeah, thank you for your question. We are looking at it. It has potential, but these are like no quick fixes, a soil that has like 4 deci can contain up to 10 tons of salt. And if you grow 10 tons of biomass with 10% ash content, it takes 10 years to remove salts. But yes, there is no one silver, bullet. We got to use different ways of managing. Thank you.
Other questions?
I have another question. I'm Amani, and my question is, so you mentioned that since gypsum is expensive, you proposed calcite as an alternative. I saw in your slide that the application rate for calcite is much higher than gypsum. I thought you said for gypsum you add about 3 to 4 tons per acre every 3 to 4 years, and it says 20 tons per calcite.
Maybe. Oh, okay. Go ahead. Sorry.
How does the price compare between gypsum and calcite, and is the availability of calcite in that large quantities that farmers will need?
Maybe I went too fast or I wasn't clear. See, calcite is already present in the soil. See, these are geological formations rich in calcium. See, in arid conditions, we have a lot of calcium carbonate deposited by the wind erosion as well as part of the parent material. So the idea was to take advantage of calcite that's already in the soil profile. And just to, these are not the rates of application. I'm just indicating how much calcite can be produced, like converted to gypsum in a typical irrigation season.
Okay, I see.
Yeah. So
Thank
the
you.
idea is to take advantage of calcium carbonate, which is already in the soil profile.
Okay, makes sense. Thank you.
Yeah, no problem. Thank you.
Hello, Gigi. This is Eugene.
Yay, Eugene.
I want to ask you one question here. So when you use the gypsum, you said the soil salinity reduced.
Right. Why use gypsum?
So so in your experiment, in your field, one side of data suggests after you apply gypsum, the salinity reduced too. What's the reason why gypsum can reduce the salinity here?
I think I said gypsum increased the salinity. See here, these are gypsum and sulfur plots at 2 different depths. We applied gypsum and sulfur to take care of, based on the ESP, exchangeable sodium percentage. the salinity of that actually went up because gypsum is a salt.
Okay, this is one side of the data. Later on, before you talk about calcite and sulfuric acid experiment, on one of those slides, you have a map showing those kind of.
Oh, yeah. So, yeah, I got it. Okay. Yeah, let me explain. This was just after 1 year. So it immediately went up.
Okay.
And gypsum is a soluble salt. Over time, it becomes soluble and gets leached down to the calcium replaces sodium, and the amount of gypsum diminishes over time, and also helps in alleviating the salinity problem. That's why this is after 4 years. This is the condition. It takes time.
Or is mainly due to the leaching from the source to lower profile?
It's not gypsum, it's the sodium chloride, I think.
Okay, great. Thank you.
Yeah. Because calcium replaces sodium and there's a lot of chloride in the water.
Okay, great. Thanks.
Yeah. Thank you.
Other questions?
I have another question. I know you mentioned that the project on remote sensing is very new and you're still working with the engineers.
Yeah.
But I'm just curious how you would take remote, what sensors would you use to measure soil salinity using a drone?
Yeah. See, that's an issue I have been asking my collaborators, because most of the sensors gather info for the surface, whereas a lot of salinity is in the root zone below surface. So I don't know if you have been following research from UC Riverside or even other parts of the country. We have been collaborating with them, and also Saurav Kumar, who is a new faculty at El Paso, is also helping me. We are looking at satellite images as well as UAS for surface reflection, and also linking that to crop, maybe NDIR or whatever indices. When crops grow in salt affected areas, within the field, you can see a lot of differences in reflectance. So if we can do ground truthing and see, hey, this particular crop is exhibiting poor growth or whatever, more red in reflectance because of salinity, and you can link crop response with the surface reflectance to identify or map the salt affected areas. That's like my understanding. I'm not a.
Okay. I was just curious. I don't know very much. I'm just curious.
Yeah. UCR has developed a lot of indices or using existing, like these indexes that can link crop response to soil salinity to map salt affected areas. And that's the approach a lot of people have been using.
Thank you.
More questions? So what's the historical trend been in terms of irrigation usage in the region over the past, say, 20 or 30 years? Is it increasing?
I think it's decreasing because of rapid urbanization. See, when agriculture fields become urbanized, a lot of water rights are transferred to city, and they use that for meeting their drinking water demands.
Okay.
So over time, and also drought and second generation growers not going back to the agriculture, and all that have affected. I think we used to have close to 60,000 acres. Now it's close to 35,000.
Oh, wow.
In El Paso County.
And so what about irrigation per unit area? Is that increasing or decreasing?
It's stayed more or less same.
Okay.
Because it's the knowledge passed on from one generation to another, and they're super afraid of reducing it. That's one reason why we have such a high, water footprint in agriculture. Nearly 80% of the water goes to agriculture.
And do you have any data on like evapotranspiration trends over the past couple decades?
I don't have historical, but we do have weather station that was installed in like 2017. But we do have one at the airport and one in the main. We have two offices at El Paso AgriLife.
So I'm wondering, as our climate is changing, whether transpiration, evaporation are going to increase in that region and maybe make this even more of a problem.
Yeah, I don't know. My guess is it has stayed similar, but that's a very good point to look at and confirm.
Very good. Other questions?
I have another question. This is Mark again. So you showed data for upland cotton, but I know Pima cotton is becoming more popular out west. Is there any data on the salinity tolerance of Pima or some of the newer varieties?
If the picture I showed on salt effects, this is for Pima cotton. This is by far the largest acreage is under Pima cotton in this area. About 50% of the irrigated acreage is under Pima cotton. You can see, on numerical data, I don't know, but you can look at qualitative information. You can see it's susceptible to salt stress. See, this is from the same field. Everything is same except for the salinity of the root zone. So I suspect it's susceptible.
Hey, Girisha, this is Tony. You throw out this slide. What's the boron levels like in your irrigation water?
It's 0.5 to 1 ppm.
And how much of that is a greater limiting factor than just the outright salinity?
I have seen, that's a good question. I have seen root zone boron levels of 2.5. I think a lot of people use 2.5 as the threshold. In many fields, I think it's still below threshold, but it might have increased over time. I didn't have an ICP until recently. My ICP quit in 2010, and I just started, I stopped looking at boron when I didn't have ICP. Now we have purchased a new ICP, and I would like to continue looking at boron concentration in different types of waters and also soil solution.
Yeah, and a lot of times we see where overall salinity is concerning, but it's specific ion toxicity that really limits crop development or even what crop options you have.
Yes, I agree with you. Yeah, it's holistic. It's just not EC or SAR, or it's also soil texture. It's like crop and everything else.
Other questions, comments? Okay, well, I'd like to thank you very much for a tremendous job, Girisha, and you're doing good work out there. Keep the salt down deep in the soil.
Thank you.
Keep it out in West Texas. Don't be sending any of it down to the lower Rio Grande.
Thank you, sir. Okay.
Thank you. Bye-bye. And for the rest of us, same time, same channel next week.